Now we have studied very carefully the area of a surface. We introduce the definition in a natural way, and then this also gives us a formula to compute the area of a surface. So the procedure is that given a surface, to compute the area, we first take a suitable parametrization of the surface, and then using the formula in the definition of area. Okay, now we consider the surface integral. This is quite simple. Let f be a function defined over a surface, continuous. Then the surface integral of f over the surface f is maybe I will write x, y, z. This is we're using the double integral to define the surface integral. The integral of the double integral is f r u v ru cross rv evaluated at uv, then du dv. So this is the definition of a surface integral. So this is the integral of the double integral. The integral consists of two parts. The first part is replace the argument of f, that is our x, y, z, by the parametrization r, u, v. R, u, v is a point because r is a map from D to R3. D to R3. Therefore, RUV is a point in R3, has three coordinates. Okay, so we can substituting RUV in place of x, y, z. And then this is the norm of the cross product. Okay. Now, for this reason, we can regard d sigma as RU cross RV du dv. This is called area element. Okay, so this is the general formula, a general definition for surface integral for a surface which is parametrization given by this map. Okay, now another class, there is a class of important surface we have mentioned many times, the graph of a function. So a particular case, if S is graph of a function g, say one function, then you can check f x y z d sigma is d f x y z x y square root of 1 plus gx square plus gy square dx dy. Okay, for the graph of a function, we know that the corresponding parametrization is this x, y, gxy, sorry. So this is g, not z. Okay. So for such a parametrization, we have known in our previous example that the norm of the closed product of Rx and Ry, that is Rx, Ry. The norm of this is precisely the square root in this formula. So, and here the xy, gxy here is simply the substitution of Rxy. The parametrization is placed as xy, gxy. So compare this with our definition. It is clear that for this particular case, that S is the graph of a function, the surface integral take this form. Okay. When we study line integral, we have illustrated several physical applications. Now, for the surface area, there are some similar examples. Okay, so let's have a look on this example. Suppose density, we still consider the mass problem. Density at the point x, y, z in the upper half sphere, that is S2 intersect with z positive, is rho x, y, z. You have an upper sphere. Upper sphere S2 plus. At every point on the sphere, the density is different. Okay. So the density is given by a function rho. Our rho equal x squared plus y squared. What this means? This means the higher the point is, the lighter, the smaller the density. In this point, at the intersection with the z-axis, the density is 0. Well, if the point goes to the boundary circle of this hemisphere, that is when the point belongs to the xy plane, then the density is 1. The largest value of the density function. Okay, so this problem. So we want to compute the total mass of this hemisphere. Okay, so we use the similar idea. So take a point x, y, z in S. For example, the point is here. Then we take a small surface element, that is a small piece of surface. A small surface element, d sigma. We take a small piece of surface about containing this point. That is, we take a small piece of the surface here. This small piece, this is our d sigma. Then in this small piece, the density is changing point to point, but because the density is continuous, and in this small piece, all the points are very close to our xyz, to our picking point xyz. So we might assume that in these small pieces, every point has the same density. The value is the density at the point xyz. So the mass of this surface element should be dm equal the density at xyz multiply the area of this surface element, still denoted by d sigma. Then integrating this mass element, our total mass of S of this hemisphere would be M equal, you're integrating the mass element around the surface, you obtain the total mass. Okay, now rho is x squared plus y squared, so we are required to compute this. So we are required to compute this surface integral x squared plus y squared d sigma. Now, by our definition, to compute the surface integral, we need to take a parametrization. So our parametrization is we can use this parametrization that is xy. This is our parametrization is r. Rxy is xy 1 minus x squared minus y squared, x squared plus y squared is less than 1. Of course, this roughly, strictly speaking, this map is not a parametrization of the surface, as we mentioned at the very beginning. When we introduced the surface, parametric surface and the surface, we use this example. We have said pointed out that this R is not a parametrization of the surface, because the partial derivative of this, which is respect to x and which is respect to y, is unbounded near the boundary of the domain, that is the unit disk. But even though we can still use this to compute the surface integral we are encountered. Okay, because we can approximate. So this is the disk of radius 1. We compute the object, compute our integral in this smaller disk. In this slightly smaller disk, this is a parametrization of a part of the sphere, but not the hemisphere. Correspondingly, this is the sphere. The sphere S2 intersect which z positive, z greater than some small number epsilon. Okay, that is here. Above the red line in the sphere picture in here. Then when epsilon goes to 0, for every when epsilon goes to 0, this blue region approximate the whole unit disk. Correspondingly, our surface, that is what we have computed, that is the part above the red line. The red line will go down. Eventually, it will approximate the whole hemisphere. Okay, so in this manner, we can use this parametrization to get our result. But we don't need to do this. We can skip this approximate procedure. We simply compute. We simply compute as the. We simply computing as if This R is the parameterization of the sphere. Okay, so using this parameterization, our M, the mass M is the integral of x squared plus y squared d sigma. Yes, d sigma. Then this will be, because d sigma is 1 plus jx squared plus zy squared dx dy. Okay, so our this integral can be converted to equal the double integral. The integral of this double integral is x squared plus y squared. This is fx fxy z, but our function does not depend on z. Therefore, x squared plus y squared. Then d sigma is the square root of 1 plus zx squared. Therefore, is 1 plus zx is minus x square root of 1 minus x squared minus y squared, then square, plus zy is minus y over 1 minus x squared minus y squared, then dx dy. So this function can be simplified. X squared plus y squared less than 1. After simplification, this becomes x squared plus y squared above 1 minus x squared minus y squared dx dy. Okay. So this, we can use the polar coordinate to compute this integral. So this is 0 to 2 pi d theta, 0 to 1. R squared, x squared plus y squared is r squared. The denominator, square root of 1 minus r squared. Then we have a Jacobian. Jacobian is r, then dr. So this integral you can compute. Of course, this is 2 pi 0 1 r cubed square root of 1 minus r squared dr. So you evaluating this definite integral, the final result is 4 pi over 3. Okay. Now we consider another example of computing surface integral. The integral is this. That is, our fxyz is x squared. Okay. How to compute this? Of course, you can take a parameterization of the surface, that is the unit sphere. Then using our definition, which also provided a formula to compute the surface integral while evaluating a double integral. Okay, but as you can expect, that will involve tedious, long, difficult computation. How to compute this integral very cleverly and very easily? Let's have a look. We note that important. I leave this to you for you to think why this is true. Then because surface integral and also the line integral are defined using double integral or definite integral for line integral. Okay, so surface integral should have some similar properties of as the double integral. For example, the surface integral of the sum of two functions should be the sum of their surface integral. Okay, so we obtain the following computation. Since these three integrals are equal, so any one of them, in particular our I, that is the integral of the x squared, would be a third of okay, but by the property I just mentioned, this would equal x squared plus y squared plus z squared, this sigma. But over the surface, x squared plus y squared plus z squared, this is precisely 1. So this is constant function. For constant function, the surface integral is precisely the surface of the area of the surface. So this is 1/3. The area of the unit sphere we know that is 4 pi. So this is the result of the surface integral we are required to compute. Okay.